So we have homework due today, so please remember to submit your third homework. So here are some here. Eyes actually you can distinguish thousands of color. Yeah, okay, orange color. But if I change to scale by your eyes, only 22 shades of gray on them. So you use color information for human image processing, very effective some classification. So color image consider part of the first is the pseudo color or some different spectrum. You can some pseudo color, hence effective object tell the difference. So the other one is the full color processing. Model space to process your color image. So pseudo color image processing is also called false color. So it's not true color. Time as your wish. Then the good image color for object. So we assign to a monochrome image. For example, object with different intensity value, we can assign to different color. Then try to enhance the object in your image. So it's easy for identification for the recognition. And full color processing, we define the full color sensor camera. So it's become very popular now. Actually, some physics issue here for the color. In fact, you use white light in front of you. Actually, contain a lot of different frequency waves, different content. So if you have a prism, this is prism, okay? So your white light goes through this prism, and because a different angle, okay, for different frequency, different wave, they have a different bending direction angle. For example, for the shorter waves, like the blue one, and their bending angle will be larger than red one. So if you have this prism, you can see clearly the white color have a different component visually. You can see it. So it's from red to blue, and so it is just give you the idea. This is found by Newton back to 350 years ago. So it's a color spectrum can be divided into broad range, okay, like this violet, blue, green, yellow, blah blah blah. So they have different frequency spectrum, but actually our visual band, we only can see this very small part of the spectrum here. Okay, the wavelengths are from 400 nanometer to 700 nanometers. Is a blue wave and red. Okay, so most of the different frequency component like a radio, TV, microwave, infrared, ultraviolet, X-ray, gamma ray, you cannot see it from your eyes. But for different animals, animals have different visual spectrum. For example, I think the bee, okay, the bird, some of the birds, they have a wider spectrum. Especially for the bee, they can see ultraviolet if they can see it. So they have a different colorful light. And some of the animal, they cannot. They are blind color. Should be say color blind. Okay, they couldn't see a lot of different colors. Can you imagine? How about the cow? You know the bullfight, right? The Spain activity sport bullfight. 斗牛, okay. What kind of the flag the human waiting for for the bull kind of color, red. So do you think the bull, the cow, they can respond to the red? Actually not. Okay, they cannot see the color of the red. For the bull, for the cow, they cannot see the red color at all. Okay, they are colorblind. They only can see, I think, maybe blue light. So how can you wave this red flag and you irritate them and you make them angry? Do you think it's the color? Not at all. So why choose red? Why choose red? Why not use blue flag? Why use red? You ever think about it? The cow, the bull cannot recognize the red color at all. Okay, to them it's just a black and white. So why use red? So how about a dog and cat you raise at your home? Do you think they can see the whole color spectrum like we see from red to blue? The fact is not. Okay, your dog and your cat, they cannot see. They only can see blue and I think yellow. I think blue and yellow. Okay, check it from Wiki or from Google. Okay, they are all color blind. Certain color. And I just tell you, the bull cannot see the red at all. But we use the red flag to irritate them. Actually not. Okay, the red flag is trying to make you proud, human, excited, not for the cow. They just notice your action, irritate them, not the color of the flag. Okay, the red color is for human, make you excited. Okay, so actually, after you understand all this content, because they have to do a lot of detailed experiment for different animals. So some of the color can have 12 different spectrum. And I think the most colorful eyes is for the kind of shrimp. Okay, so like a peacock shrimp. Okay, they can see 12 different cold vision or style. Their eyes have different 12 different colors. Okay. And most of the animal only have one or color blind. For human and monkey, we have three colors to look at. We have three different cone cell. Okay, we will see it later. Okay, we have a blue, and we have green, we have a red cone cell, so we can recognize these different three primary colors. But most of animals, okay, your dog and your cat only can tell the difference from the blue and yellow only. Okay, this depends on their physical cell. Okay, so I think this each color is characterized by different frequency wave. They're wave. Okay, they have different wave. You can see it. Yeah. So the wavelengths comprising different visible range of the electromagnetic spectrum. Okay, and let's see the different colors in the spectrum do not end abruptly. Okay, so they're very smooth, blending together. Okay, so it's smoothly into next one. And the color perceived by human depend on the nature of light reflected by object. Okay, so you see the red color because the object is the red component reflect into your eye, so you can see it. And the object appear green, reflect the light only in this range. Okay, from 50 to 500 to 570 nanometer range because it's green color. Frequency and wavelengths. Okay, and characterization of light is important for understanding of color. So you have to know what is light. Okay, so light actually we have this different element. Okay, the light is achromatic. Achromatic, which means no color. Okay, so devoid of color. Take away the color, we call achromatic. And chromatic is color. Okay, and you add one more character in front of that. Achromatic is no color. Okay, so it's only attribute of its intensity. So if you take away the color from what you have seen, it's only intensity, amount of light, only light. Okay, and this is what we have been dealing with so far. And we all have put in previous chapter, restoration, enhancement. We only focus on grayscale image processing. So we call it achromatic image processing. And the term grayscale refers to scale measure of intensity of the light, only the intensity, okay, of the light, and black to gray to white. So we have normally we have in your computer, you use 1 byte to present it. So you have a 256 different grade level scale. Okay, but now we are going to look at the color spectrum. So we are going to take care of this chromatic light. So the chromatic light span is EM spectrum from 400 to 700 nanometer, the wavelength. So the inverse is their frequency, their frequency. Okay, so the larger nanometer, they have a low frequency. For the violet, for the blue, they have a higher frequency. So after that is ultraviolet, sometimes harmful to your eyes. And the basic quantity are used to describe the quality of chromatic source, including this. Okay, so we are look at the chromatic source of light. How you describe it? The first one is the radiance. Okay, the radiance. Radiance, what is radiance? Radiance is the total amount of light flow from a light source, measured in watts. Okay, and the luminance, Liumin, okay, is give a measure of amount of energy. Okay, so it's an observer received from a light source, actually measured in lumen. And here is maybe you have used the other luminance measurement. We call it luminance intensity. Okay, the other popular general using is the luminance intensity. We use this candela, 烛光, to describe it. Okay, and per meter square. Okay, CD is candela. Okay, or candela. Okay, anyway, 就是烛光. Okay, so it's in the unit area, you have how many energy amount of light energy, and it is luminance intensity. And luminance they use the lumen to as the unit. So what's the luminance luminance flux? Okay, and the relationship with lumen and the candela. Actually, the 1 lumen equal to 1 candela times Sturdian angle. Is Sturdian angle. Okay, so the Sturdian angle is just like a sphere, a ball. Okay, a ball have a 4 pi Sturdian angle, Sturdian. And so 1 lumen. Okay, so in physics, I just tell you, just know about this concept. 1 lumen is equal to 1 candela times 4 pi Sturdian, because it's a whole ball, and it's about how much it should be around 4 pi is I don't have this number 3.14159. Maybe 12 point something, I forgot. 12 point something candela per square. Okay, CD per meter square. Okay, so which means from 1 light source and radiate to whole different angle, and it's 12 lumen. Okay, so it's kind of to measure the amount of energy of light. Okay, so another one is brightness. Actually, brightness is just a subjective descriptor. We just mentioned by human, by dog, by cat, by fish, by bird, by insect have different different subject to describe it. So there's no specific measurement for brightness. We always call this together. Okay, so luminance and brightness to say the energy of the amount of energy of the light. Okay, so just that you know, there are some chromatic measurement and radiance measurement, luminance measurement. Okay, so briefly, in our eyes, we say in your eyes, the bottom of your eyes, there's a retina. Okay, 视网膜. Okay, on this organ, they have about I think 600 million, 6 million, sorry, 6 million, about 6 million to 7 million cone cell in your retina. Okay, and this is like the cone shape. Okay, so in your retina, and the other one is a rod cell. Rod cell. It's about I think 120 million. Okay, rod cell. The rod cell we mentioned is only can detect the from from intensity gray label. There's no color. But the cone cell, we have 3 different type of cone cell for human being. Okay, we have a red, we have a blue, we have a green. So it's a kind of your receptor. You can see it in this colorful word. So it's basically the cone cell provide you color information. But maybe some genetic problem when the baby born with some problem with this different cone cell issue, they will become blind or with blind color. With color blind, I mean maybe they cannot tell the difference of the green and red. A lot of it should be maybe 10%. It's pretty high prevalence rate for the color blind. Sometimes a week. Okay, so I think you already have a test during your when you are a kid. They have a different color spot and with a number on it, and you have to tell what's the number on it. If you cannot tell because your cone cell have some problem, you cannot tell the difference between the red color and green color. So it's all because the cone cell. The cone cell will help you to recognize the different color. For human being, I just tell you, we have 3 different types of cone cell: the red, green, blue. And for the dog, they only can tell the blue and the yellow. Their cone cell can recognize different frequency of the light wave. And 60 million to 7 million cone in the human eye can divide into these 3 different categories. We just said red sensitive. So your cone cell have higher percentage of the cone cell in your retina, and green cell only 33%, and for the blue only 2%. Okay, so the later one is the most sensitive. So here is just absorption of light of the different cone cell in human eyes as a function of wavelength. So you can see different wavelengths. We just mentioned we can observe the light of light source. The wavelength is between 400 nanometer to 700 nanometer, and the blue is around this one. And they are not only spiked; they distributed in a normal distribution shape. And this is their absorbed representation here. So if from your red, your green, and blue, and you can see the color here. And for a standard representation of this color, so the wavelengths we run these 3 primary color are established by standardization committee. We call it the International Commission on Illumination. Okay, so why we have this standard? Because every different light have their different representation, so we need a standard. So the corresponding to the experimental curve can be represented. Okay, so these are specific color wavelengths used mainly for standardization. Okay, so actually here are some examples to look at this standardization. The most important we know we have 3 primary color, right? But you have to look at it. It's for light or for pigment. Okay, so we have 3 different primary color. Okay, we mentioned we have a primary color. Primary color. So, but you have to look at you are using additive system or subtractive system. The first one is for additive. We call it for light. Primary color for light. Okay, so it's an additive system. So your primary color is the RGB here. RGB, red, green, and blue. And how they combine together to a new color. So here is the mixture of light here. If you have the light, okay, 光源, okay, you just project this different color, the green, blue, and red together. Finally, you will get, if the light is equivalent, okay, the intensity, luminance is the same. Add up, they have the white color. So this is the present. You can see they decompose the white color into different components. If you add up these 3 light together, you get white. If you add up green and the red, you get yellow. If you have a blue, green together, you get cyan and the magenta as well. But if you have a different primary color system for printing, for pigment, actually we say pigment. you know it's like printing. Okay, use your printer. So if this is the primary color system for printing, it's totally different because the primary color is not a green, blue, yellow, blue, green, red anymore. The primary will be yellow, cyan, and magenta. That's the reason why your printing printer, you have to buy a cartridge in this CMY color, okay, and the one more black color, okay, there. So this is the primary color for pigment, okay, for printing system. So this is, we call it the additive system. The other one is the subtractive system. So it's totally different. So which means if you use primary color for pigment, for printing, and you mix all these three colors together, so you have your color pen, okay, straight tie, and then you put the yellow, the primary color, magenta, and cyan, and mix together. They are equally amount and mix together. The end up will become black. Okay, so that's what your experience when you are a kid. You are drawing and you put a lot of color together. It's become black. It's not become white. Okay, so the white is for the source. Okay, so remember your primary color system is different. It's dependent on if you are looking at the light or pigment. Okay, so primary color produce second color. Okay, so every different color system have a secondary color. Okay, for this one we have a secondary color, and for this one we also have a secondary color. So how you get a secondary color? You just add up two of them, and you will produce the second color system. For example, for the light source, and you will add red and blue. So we say we add red and blue, we get magenta. Okay, so the light magenta becomes secondary color of the lighting system. And if you see red plus, so it's all playing around like this. Blue plus green equal to 1. Okay, if they color together have the whole system white light. And you can see one take away red and the blue, it become green. So you can see it's a corresponding system. So we can say it's one minus yellow. What's that? Okay. So it's a 1 minus green. Okay. 1 minus green. 1 minus green is the magenta color. Okay. And 1 minus green is magenta color here. 1 minus green is magenta. So you can see from the system, green here, corresponding secondary color is a magenta. So from this graph, you also can recognize their relationship. Okay. And also green plus blue, it should be signed. So green plus blue, green plus blue, it should be signed. And it's also 1 minus red. Okay. So it's second color system and their corresponding second color. So red and cyan is in this location here. Mixing this primary will get a secondary. We just mentioned with its opposite primary. So we just say it's an opposite primary for your secondary system. So primary color of pigment we just mentioned is different from the light. Okay, it's a subtractive system. So you have a CMY, and it's actually the similar operation like this one. Your secondary color for the pigment for the printing is just you use two of the color plus together. You create the secondary color of your pigment color system. So therefore, primary color pigment are CMY. So you just remember for the lighting is RGB. For the painting is CMY. Okay, mixing all this pigment will get the black for the subtractive system. The normal light you use, the color system is for the lighting is television. Okay, there are a lot of LED. They just eject the light and combine different color system for you. And the other one for the printing is for the pigment, color of pigment. We mean the subtractive nature system of the color, the pigment. So it's two example you can see how to use the different color system here. Okay, so let's see how we describe the distinguish one color from the other. So we have different color model. Okay, that we call it HSI. Okay, so HSI color system. Okay, H is the hue. Okay, hue is the 色度. Okay, it's a attribute associated with the dominant wavelength. So we have a different wavelengths of your color component. So we call it a hue system. Represent dominant color as perceived by observer. Okay, so you can see the hue of the red, hue of the violet. And the other one, HSS is the saturation. Okay, this is very important color model because it's for description of color. So you never use RGB color model to say color, okay, because we cannot communicate with that. I just give the example. You cannot tell me this student wear a clothes of the color is R equal to 200, G is 100, and B is 50. I don't know what you are talking about the color, but you can say it's a light blue, it's a light brown. Okay, so it's talking about this in color description. So we use HSI model. The S is the saturation. Saturation is the relative purity of the amount of the white light added up with the hue. So you have a pure, the hue is the pure color, like red, like blue. Okay, it's a fully saturated. But if you add up the white light in this color, this is a full saturation color. So we mix it together. We say we have different saturation color, different saturated color. So it becomes light blue, lighter. Okay, because you add up white light in it. Okay, so maybe you have the red one with the white light, it becomes pink. Okay, become lighter. Okay, not so full red, saturated red. So like the lavender is a 薰衣草, is a kind of a light purple. Okay, so it's because you have a violet plus white, and then it's become less saturated. So you describe the color in your communication. So you say there's a light red, okay, light blue. We know you are talking about the saturation, okay, the saturation of the color. The next one is the brightness or the value. We call it intensity. The body is a chromatic notion of the intensity. So it's what's the intensity of this color it is. So we can see we use this color model for describe the color. We call it the HSI model. Okay, hue, saturation, intensity. Actually, sometimes intensity, you know, it's a brightness of the of your color brightness. So here is from 0. The value is like this way, from 0 to 1, very shining, very bright, or very dark, and you have different color hue. Okay, different color hue. Hue is in 360 degrees in the circle. Okay, from red to blue. Okay, located in this hue circle, and this is the saturation. Saturation is how much white light you add up in your pure color, saturated color. So we can see if you don't have a white light, it becomes dark. If you have a lighter one, your bright, your intensity higher, and you have a full saturation color here, and you add up white color in here, so they will change the saturation. So to the middle one will become white one. Okay, so you just add up the white light to your pure color outside this one, the hue, and the center part is a less saturated color. Okay, so this model is a more normal one we are going to discuss when you communicate with the color system. Okay, so how can we describe it? I think back to this kind of CIE model. Okay, is back up to 1931, the standard color, and for this system. Yeah. So how you can describe their number? So they use this tri-stimulus. Okay, stimulus is the human retina stimulus. Okay, so because we use human 3 different cone cells, so we have different stimulus. Okay, your reaction from your cone cell. So tries, which means 3. So you have 3 different functions to describe the color. So we have the XYZ. Their stimulus denoted by XYZ, capital XYZ. And in general, color can be specified by these 3 coefficients, trichromatic coefficient, like the X. So you add up all these your stimulus, and then for the X color, you have Rx in the numerator, and the Y is like this one. So you can see X plus Y plus Z equal to 1, total color system there. Okay, so by that one, we will see this chromatic diagram a lot. Okay, so it's also the standard from the CIE, Standard Organization Committee, and we will see this tongue shape. We call it a chromatic diagram. So you can see at the corner, at the surrounding, it is a full saturated color, and in the center is there's a equal energy, point of equal energy. So in X, the axis is we call X, we just have the coefficient, right? Tri-stimulus coefficient. This is Y. So Z can be calculated by 1 minus X minus Y. So in this CIE diagram is very useful. So you can see every color there. In the surrounding area, it is a border. The border of the tongue shape is the fully saturated color. And if you want to look at green, where is the green? You can see the green, and then look at the XS. So it's about, I think it's about what's the number? It's if you draw this for the green, X is 25 for green. For green color, this point for green here, for green. If you look at this CIE diagram, so the X equal to about 25%, and the Y around Y shape here around 62%. So you know for a tri-stimulus coefficient Z equal to 1 minus 25 minus 62, so equal to around 13% for the Z tri-stimulus coefficient there. So every different color, red here, pure red, blue here. So you can just look at the coordinate and you know the component of the color. So it's a standard committee define this tongue shape. We call it a chromatic diagram. So it's very important. You can see it everywhere. And if you have an equal energy, what's the equal energy? We say it's 33 for the X, 33 for the Y, and Z for 33.3. Okay, so the will be here, this point. 33, 33.2, 33. See, it's a point of equal energy. Actually, it's a white color there. And all the line around here is warm light, cool white, and warm white. It's all white color, but in different way. Okay, it depends on your stimulus coefficient. We have a lot of different white. Okay, warm white, cool white. Okay, and you can see from this color diagram, you can do a lot of different analysis there. Okay, so we will please look at this is the CIE standard, and yeah. So now let's look at your device at your hand, your cell phone. Your LED in your cell phone, they only can produce the pure red, pure green, pure blue, right? So it's a pure green here, pure green, and blue and red here from your LED. So you will try to observe how many colors you can observe from your cell phone. So it depends on your LED where it is located, because all the color combined color will only happen in the center of this triangle. Depending on your device, is this good LED or not? So you have different location, and you can represent how many different colors at your device. So within this triangle, that's what you can see from your device with this standard primary color device LED. And what's the inside of this gray color shape? This is for printing system. So, which means your printing color is much less than what you can see from your mobile device or from your TV. And a lot of color you cannot see it from your device at all. That's the rule. So it depends on what the device you are using, and is this a light source or is a printing? So a lot of different. This irregular shape is only the kind of color you can present from your printing device. Okay, so it's limited. So although we have so colorful CIE diagram there, but not all of them you can obtain from your device or print out from your device. So we call it a gamut of color. So it's in Chinese we call it 色域, okay? It's a range you can do, okay? A gamut of color, but what you can see from your device or what can you print out from your device is limited color, but the original color should be like this 4 color space here. Yeah, so unfortunately, all our devices have some limitation. So let's look at the color model we just mentioned. We have the purpose of a color model. What is this purpose? Because we have to try to facilitate the specification of color in some standard fashion. So a color model is specified in a 3D coordinate system. We are going to use this color model in 3D because we have RGB, CMY, blah, 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 HSI. Most color models used today is based on hardware or some application of this involving color manipulation. The image processing, the hardware-based color model mainly use RGB, CMYK, and HSI. So now you know the most popular system is RGB for your light source, CMYK for your pretty device, HSI for your communication. Okay, actually in your TV we use YIQ. So it's a different color model system. And also maybe you heard about the YUV. Okay, this is similar to YIQ. Okay, this is the TV system because in previous we have a black and white television, right? We are nowadays no one see the black and white color TV. We always have colorful. So, however, this is a very good representation for the a grayscale TV. So it's a white there. We'll see the coefficient later. So RGB, we just know it. CMYK, we know it because the black is difficult to present. Okay, so CMY is not enough. So we have a CMYK instead. And the HSI, which mentioned, is a hue, saturation, intensity. Okay, so it's a color model here. You can see RGB in this 3D, very easy to look at it. So you can see if we add up together, this should be white because 4 red, 4 blue, 4 green add up together. So here, so it's a 1, 1, 1 here is a white color. 0, 0, 0 here is black here. Okay, so if you draw a line between these black and white, so it's a gray label. It's always a gray label because every different primary color equivalent. So in that sense, it becomes a gray scale, and from black to white in this diagonal lines occur here. So it should be very easy to understand this RGB color. And we just have this cyan, yellow, magenta, right? If you go back to look at this 3 primary color mixed together, and if red is 0, no red, and only blue plus green, we get cyan. Only green plus red, we get yellow. Only blue plus red, we get magenta. So it's just like the three primary color circle in previous graph. Okay, so it's use 3D much be easier. Okay, so if you draw all these color together and then put it in television, and you can see we have how many color. If you one color RGB, use 8 bits to represent it. Okay, every color we use 256 color to present it. Okay, change to different one. Actually, just change this to 256 different color label, 256 color label. A total of 16 million color you can represent in your system. Okay, so it's we call it a 4-color image. Okay, 4-color image. So it's like this color system here. So for this one, it's RGB. Okay, RGB here. So we have a RGB. If you use color system from this original one, and you can see the color of this primary color image. You will look at it like this different RGB system there. But to tell the truth, because different devices have different ability to present it, so sometimes we are afraid it cannot fully describe the color you want to describe. So we change this one 8 bit to only six color in web service. Okay, make it easier. So because we just mentioned, even your eyes, you cannot tell them much different, but we can give a set color as a standard. So every color to use six different colors to present, we call it set color model. Okay, all systems set color model. So as we call it a web color. And how you do it? You just have every color. We have a 6 different representation. So what does that mean? So we have a 6 times 6 times 6 in RGB. So how many colors we have? For the web set color, actually we only use 216. Okay, sorry, this is wrong. This is not 2 to 6. It should be a 6 to power of 3. Okay, so actually every primary color, you just use 6 of them. And what's that? It's like this. Okay, in each number, okay, 0 to 256, you separate it to 6 different colors, and for the RGB, all the 6 different colors to be presented. So in the web, we use this standard set color mode, only 215 color, like what? Like I should here. So you can see this parrot a lot, right? Actually, it's only 216 color in this table there. And this is the gray label. Okay, so if you have the same color there, so a total of 16 gray label you can see from the web set color. Yeah, this is just give you some idea from the color space. If you just take the cross section from the one, and you will see this representation like this: R equal to 0 from the cube, G equal to 0 from the cube, B equal to 0 from the cube. So actually it's just a mix, no big deal. And for the color set web color is set web color is 216, and you just make this a cube into 216 small cube. Okay, so it's we call it RGB set color. Another one is CMY. I think about the CMY is most of students didn't know that one, but now we mentioned you have to know, because your printing system, you can only buy cyan, magenta, and yellow cartridge. And how you get it? We mentioned it is a second color of your primary color of light. So you just use the original one minus R color component, you get a C. 1 minus G component, you get magenta. 1 minus blue, you get yellow. Okay, so you just remember RGB, CMY, and they are primary system, secondary system of the light, and you just say they're just the other side of it. So it should be very easy. But how about the CMYK? We just mentioned we have CMYK. So how can you do it? So actually CMYK is the issue to do this one. You have CMY first. You change to CMYK. Okay, so there's a new C, M, Y, and K. So if you use some to make the differences between them, okay? So how you change it? It is very easy from RGB to CMY, right? Now we are going to change to CMYK because we have a new break, the break color is in our CMYK system. So the rule is like this one, okay? So we just choose K equal to what? Minimum of CMY. So now I give you the CMY system. I give you a C color, M color, magenta, a yellow color. How can you transfer to CMYK? Okay, CMY is easy. If you got the RGB there, it's just 1 minus that, you get it. But now we are going to change to CMYK. So how can you do it? So it's depend on your color of break. So first, try to find the minimum of the CMY. The second, just look at the K. If you want to represent it's pure break there. So if K equal to 1, it's we call it a pure break. So what's a pure break? It all mixed together. So there's no other component at all. So at that time, the C prime equal to Y prime equal to M prime equal to 0. Okay, so this is the only one condition. If you use a break in your system, you want to represent this K color, it must be full saturated color break is 1, and all the CMY, the new system, will be 0. Otherwise, Otherwise, what's the CMY? It's you can calculate this one. It's a C minus K divided by 1 minus K. It should be very easy to think about it. So M prime equal to M minus K, 1 minus K. Y prime equal to Y minus K, Y minus K. So this is a way you transform your RGB to CMYK. Why? We just tell you. When your K is not 1, if you look at it, if K equal to 1, what's the result? If K equal to 1, what's the result? If K equal to 1, you cannot use the denominator 1 minus 1. It becomes 0, it becomes infinity. So that's the way we have to separate two conditions. If you are pure gray, there's no CMY pure, because it's purely saturated gray color. From Y prime and prime 0, right? If your K is not 1, which means there are minimum of this color, CNY minimum of it. So it should be less than 1, right? So 1 minus 1, 1 bigger than K, and C minus K. So you can see, can you add up together? So C and Y add up together. These three add up together. What's the result? Numerator is the same, 1 minus K. And you can see if we add it together, if CNY, wait, another way. You have K is a minimum number there. So should add up should be 1, okay. C from N from Y from. Try to calculate it one. Because we have one more component K here. So from here, C your original minus K, so okay. So come on, CMY will end like here. So if you go back to change it CMY to back to CMYK to back to CMYK to CMY, how can you do? Just do this one, like it, Y minus K, Y prime times E1 minus K, and the Y equal to K plus Y prime 1 minus K. So from here, you can get this one. So actually, these are three different systems. You can change it around. RGB, CMY to okay, depend on which kind of system. Okay, you can give some do example there. I just give you two conditions. One is pure break. This pure break can become nothing left. So C prime Y prime new system will be 0. And if it is not, we have some smaller. We just pick up the smallest CMY as K, represent K component, and then calculate the other three components like this approach. Okay, so for example, like this flower, if you want to look at their CMYK component, it's from RGB. It's easy. It's just 1 minus R is C, 1 minus G is N, 1 minus G is Y. Okay, so we get this three image. So you can look at the cyan image of the component, magenta, and the yellow component of this one. YIQ color will just tell you it's a TV system. So TV system, so they are very important for the gray exactly, very accurate gray label. So it is not 1/3 of that one. So it's some specific component. So it's also defined by the standard NTSC system here. Okay, so it's defined by this television standard committee. Okay, so they have very accurate coefficient for the RGB component transfer to Y. So Y is the gray label intensity. I and Q is corresponding difference chromatic color. Okay, so it's a quadrilateral component, inverse component. Actually, is for color description, and this is for black and white, the gray label description. So it's a YIQ color model. Sometimes you have a YUV. It's different coefficient, but they just shift to center, so they have to minus 128. Okay, if your label is 255, so there's just some shifting issue. Anyway, so we have all these different color model here. This is the IQ for the color system. So it's based on this transformation. So we have a lot of color model. We can transform from one to the other one. So next time we will see how to transform to HSSI, hue, intensity, and saturation. So it's different way because it look at different hue angle. Okay, so let's stop here. We'll continue next week. So remember, today you have to submit your homework 3. It's very easy. We didn't finish yet. So go through our code. It should be very easy. Okay, so stop here. 好，好，怎么样的？